Okay. The only difference is I have to, if it allows me to do it, is I have to, you know what, I'm going to get rid of this. I have to redraw this because the orientation is not the same. Okay, I'm going to get rid of this. I'm going to get rid of this. Okay. I'll just use the axis. So we know that, right? We know that this is under axial loading. This is Px over A. Okay. So based on this diagram that we see, on top is under compression, below is under tension. So at the top is under compression. So now the orientation change. So now the orientation is this way now. Okay. So you have compression. And you have tension. Okay. And this is due to bending moment. Where you have minus mz over izzzy. Okay. And how does the final one is, how does the eccentric symmetrical bending look like now? Okay. When eccentric symmetrical bending, so this is still our stress x. Okay, so the formula now is equal to stress x is equal to px over a minus mz over izzzy. Okay, so basically we add both of them together. So now this is our axis, right? Y. So I just copy the gradient and then I shift the gradient towards the right. Okay, towards the right. Okay. Why towards the right? Because the px over a is in what? Is having an additional tensile. Okay, so from here, this is the compression, and then down here below, these are all tension. So what you see over here is there's a shift, or the so we are aware that over here, this is the that's not a good position to put it. At this point where y is equal to 0, right, is the position of the centroid. Okay, of the centroid. So remember, I told you the centroid is a geometry feature. You use geometry to find. So now we can see that the neutral axis has been shifted. So this is the position of the neutral axis. Okay. So for eccentric bending, right? And I did explain this before. So for eccentric bending, symmetrical bending, the centroid and neutral axis are not on or are not in the same position. Okay, they are not in the same position at all. Okay, now let's look at another example. Okay, let's look at another example. So this is our example number 3. Okay, let's look at example number 3. So I'm going to, as I said, the example I can find on Avenue. Copy. And we're going to get the diagram. Okay. So now, knowing that the clamp shown has been tightened on the wooden plank, okay, and been glued together until P reach 400 Newton. So we know that P is at 400 Newton. Okay. Determine in section AA the stress at point A, the stress at point D, and then ask us to locate the location of the neutral axis. Okay. So if we were to sketch our transformation, right? So this is our X, and this is our Y, and this will be our rotation about Z, right? And on the right hand side is our cross-sectional view. Okay. And the cross-sectional view over here, if we were to sketch out our transformation, this will be our Y, and this will be our Z, and over here, this is our rotation about X. Okay. So there are a few things that we need to do, right? So we know that this structure over here is under eccentric symmetrical loading. So some of you will ask me, Eugene, how do we know, right? That is eccentric. Okay. So a good thing to find out. Okay. If I were to sketch the position of the centroid, okay, position of the centroid. So this is the position. This is just a sketch. Okay. So this is the position of the centroid. Again, I say this is just a sketch. Okay. So this is the position of the centroid. And that position of the centroid relative to the cross section, again, this is just a sketch. Okay. So it's exactly at this position. Okay. So this is also our centroid. We don't know where is it yet. We have to find out. Okay. And if the axis of the centroid, or when what you see when the axis of, or when the centroid is parallel to the applied force vector, Okay, then the loading is under or is eccentric symmetrical. Yeah, I should not call it loading, bending. Okay. Okay. So for this case, we know that the formula that we have to apply is stress X is equal to P over A, right, minus MZ over IZZ multiplied by Y. Now, as I said, I don't want you all to worry about the plus minus sign down here. Okay, I don't want you all to worry. I teach you how to visualize. Okay, so what we will tend to do, right? What we will tend to do is we will sketch. Okay, the next thing we're gonna do, we're gonna sketch the deformation pattern to determine the moment vector. Okay, so from here, I'm gonna take this image, right? So when this structure deform, okay, when this structure deform, the deformation will look like this. And I'm going to sketch this out in orange, right? The deformation will look like this. All right, P is acting this way. Right, P is acting outwards. Right, so you know the moment vector is going to act this way. Right, and this is moment about Z, moment about Z, and then you know that the head of the moment vector is going to be compression. The tail end is going to be in what? Tensor. So from here, you know that point D, right, will be going through compression, and point A and B, depending on the position of the neutral axis, okay, depending on the position of the centroid. You don't know where the neutral axis is yet. Where the centroid is, you know that above it will be under what? Tensor. Okay, so that's the easy part. Or not, sorry, I should not say easy. This is the analysis part. Okay, you have listened to me for an hour. What I propose is we go for a short 5 minutes break.